So we'll carry on talking about the topics of being able to figure out exactly what's going on in the subsurface to see if you have a reasonable play or not. And so the second topic that we will cover is talking about geophysics. I just pulled up on my browser a report which is perhaps quite useful for this class in that it looks at it's right behind here. It's the web link that's on these notes, and it's actually the site investigation, the phase 1 report for what was the Forge site. So the DOE Forge program, Frontier Observatory and Geothermal Energy, was a competition between a bunch of different proposers. Some were, one was this place, west flank of Coso, California, which is down west of Death Valley and east of LA, in that kind of region, which is an existing geothermal field. And the deal for the Forge project was that it had to be a non-hydrothermal field, so hence this was located on the flank of the operational hydrothermal field, where the permeabilities were low, but temperatures were still high. And there were probably 5 of these reports for 5 different projects vying after it. The winner was Utah Forge. You'll hear from Joe Moore, a recorded talk a few weeks after spring break. And this goes through all kinds of things that you typically do at a high level to be able to figure out what's going on in a geothermal field. And I won't go through it. It might actually be quite useful material to talk about, but it's really putting together the picture of what you have and being able to evaluate things both from this site, which has existing boreholes and drilling on it, and has existing geophysics, and has existing production, so at least you have an idea of what's going on there, and you know something about the geology as well. And so we'll talk about some of these things that add to the database, and you'll see arrayed there things that we're slowly getting to. So we talked about having a big picture view of geological habit, which was last time. We talked about the geological setting. Today we'll talk about using geophysics to be able to prospect for what might be in the subsurface. We will talk on Tuesday online about drilling to be able to retrieve cores, and also about being able to do pump testing, which we've already alluded to in some of our simple models of geothermal systems, maybe in topic 3 or 4. I can't remember. So you'll see some of these things here using drilling data, well data, pumping data from wells, and using things like existing earthquakes to decide on, if you have earthquakes, you probably have strains that open permeability that make your system viable. Very few geothermal systems have no seismicity attached with them. And so all the things that you might want to be able to understand about your system to be able to define whether it's viable. To figure out what the stresses are that are there, because those control whether fractures are closed or open. To see whether it's hot or not at shallow enough depths. You don't want low permeability, but in the Forge site, this was to benchmark the possibility of having a demonstration project for EGS projects, which by definition are in low permeability rocks to start with. And so that was a requirement for this. And then you stimulate them to be higher. And then you look at some other, just another requirement for Forge was that it couldn't be a hydrothermal system. It could be on the flanks of a hydrothermal system, but couldn't be a hydrothermal system per se. And so that's something that's perhaps worthwhile looking at if you want to look at this stuff more. I imagine you probably won't. It's not a big deal to me, but it's at least something there that's a resource if you want to make use of it. And so we are coming back to the same requirements before. We like to make sure before we invest a whole bunch of money that we have a viable site. A viable site means that perhaps we have fluids that are hot. We need both of those to be able to work in most of the things that we're talking about. And we want to know what the rates at which we could produce fluids and what temperatures we might have. And so geophysics typically won't tell you anything about this, but it might tell you about the presence of fractures and faults, which might be good indicators, for instance, of the ability to be able to move fluids. And so that's a necessary component. And of course, if you're going to engineer the system from start and just have a cookie cutter approach, a bit like shale gas, drill a shale gas well into the Marcellus, you go down 3 kilometers, you have a lateral that goes a couple of kilometers out, and you just frack the heck out of it, you're almost guaranteed that you can get a productive well out of it. Likewise for ground sourced heat pumps, there's heat at 10 feet depth, 3 meters, 4 meters depth. You're guaranteed to have 55 Fahrenheit temperatures, and that's all you need to provide a sink or a source for your ground sourced heat pump. So these are different from the ones that we're talking about now. The ones we're talking about for hydrothermal reservoirs and for EGS reservoirs as well, to some degree, we'd like to be able to know if there's prospects of us being able to get enough flow in the system, even if we expect that we have enough temperature. And so that's what we're interested in. So the next method after just thinking about the geological setting is geophysics. And geophysics are all methods that use a proxy to be able to say something about the subsurface. And the geophysical proxy is either looking at the magnetic characteristics of the subsurface, the electrical conductive or electromagnetically conductive conditions of the subsurface. Electromagnetics would be radio waves, so it's like radar. The acoustic properties or seismic velocity contrasts in the materials in the subsurface. The density contrasts, which would show up if you have low density materials versus high density materials next to each other. And so all of these use those items as a proxy. So you don't look for the permeability itself, but if you think you have permeability and water in fractures that might have brines in them, then they might be electrically conductive. And therefore, if you find a conductive zone, it might be an indicator of that kind of behavior. And so these are all methods that can be applied typically from the surface. And borehole methods are methods, not surprisingly, that are applied once you've drilled a borehole. And you typically use these to measure the magnetic susceptibility of the rocks, the conductivity of the rocks, the seismic velocities of the rocks, and their densities in boreholes to be able to correlate with the values that you think you've recovered from your surface investigation. So that's kind of the way of doing it. And so really these geophysical methods are all surface-based methods for the first 4 that we'll talk about, and then using a borehole instrument, a sonde in a borehole, to be able to correlate them in the final one. The whole idea of this is that geophysics, you'd like to be able to understand exactly what's present in a big volume. And so this volume might be, say, between 2 wells for an EGS project. It wouldn't be unusual for that distance to be of the order of half a kilometer. And so the scale of this is quite large, perhaps a couple of kilometers on edge. And obviously a borehole, if you drill it, gives you a very good picture of exactly what's there, because you typically recover drill cuttings and perhaps core, but you only have a picture along a very narrow corridor. In surface investigations, such as for ground sourced heat pumps, it might be easy to dig with a backhoe. You could probably get down 10 feet and you can see exactly what's there. You probably don't need to. I guess you might be interested to know if you have big boulders, because you wouldn't be able to put the heating coils in very easily if you have a really heterogeneous system, but that's perhaps not very interesting, probably not very necessary if you know that you have some soil. But if you're looking at a big site, then geophysics is perhaps the way to have a big picture view of the whole site on itself. And that's kind of what we're talking about. And we'll talk about each of these 4 methods in turn as we go through, and then finish it off with understanding exactly how we can corroborate the proxies, magnetic susceptibility, electrical conductivity, or dielectric constant for radar, seismic velocities or densities, how we can get those from corroborating borehole wells, which we'll talk about next Tuesday. And so this is kind of the same idea. So a core sample that you take, size of your fist, it's not very representative of a site if the site is a couple of kilometers on edge and for these sites that we're talking about, say 5 kilometers in depth. And so the only way that you can get a picture of that at the big volumes is by using geophysics. And so what we'll just do is we'll step through those 4 different methods and kind of talk in general about them. These notes are not meant for geothermal exploration per se. They've been slightly augmented for it. It's for another class on contaminant hydrology. And so some of them are more specific to near surface exploration, say within the top 10 meters of the soil horizon, rather than the top 5 kilometers. But the principles are worthwhile at least understanding, and understanding how they might or may not fit into kind of geothermal prospecting. So geomagnetic methods look for the magnetic characteristics of the subsurface. That might be iron ores, or more likely for looking at environmental geophysics, looking for Jimmy Hoffa in his 55-gallon metal drums. So it finds iron targets, and it's based on the idea that if you look at the Earth's magnetic field from pole to pole, it's arranged so that these lines, streamlines of magnetic flux, if you like, because of the dynamo which is in the core, and there'll be equipotentials attached to these, but they define some natural magnetic field that's put together by the iron core of the Earth, and it uses the lines that travel, electrons that travel along those lines to be able to define that electric field. And if you put a target in there which is iron-rich, then the magnetic field will prefer to go through that iron-rich target rather than just material that's non-magnetic. And so there'll be an anomaly that you can pick up in terms of the magnetic field close to this location. So it'll tend to bunch the flux through this middle zone, and it'll be depleted either side. And so if you take a magnetometer and run across the surface and look at the magnetic field, defined in terms of Teslas, nanoteslas in this particular case, then depending on how high above your target you are, you'll get a certain degree of definition. So if you're very close to your target, right above it, in other words, then you might be able to pick out individual features of drums and spaces between drums in this particular case. And as you get progressively higher above it, so this is 0.2, 0.5, 1, 2, and 4 meters above it, then you start getting a much less granular picture of what's going on as you get higher above it, because you're getting in the zone where you're not really in these bunched lines of magnetic flux, and you're back up here as you move higher up. So it makes sense that you have less view of what's going on as you get further away from it. So certainly you can find things by looking at this. Where you have peaks, you'd have high bunching of the streamlines, and therefore the location of a target somewhere close by underneath. And it turns out that you can actually be much more quantitative than that. And the idea is that where these lines bunch together, you will get some kind of anomaly of a peak where they bunch and a depletion on the other side. And if you find your target and locate it relative to the peak and the trough within your profile, as you take your magnetometer and walk it across this system, then you can use that to say something about the distance between peak and trough being something like double the depth of your target below the surface. So somewhere between the peak and trough, not exactly aligned with either of them, but at some depth below it. So you can use it in a quantitative way to be able to locate your individual components. Doesn't really apply to geothermal systems because there's nothing in geothermal systems that would speak to that. But the idea is that you can take an instrument which is either a permanent magnetometer, put it on the ground, measure very accurately the vertical and horizontal components of the magnetic field, and at some very high accuracy, and be able to construct a figure like this. Or perhaps more usually, which is often used in exploration, use a proton magnetometer, which is much simpler. It's usually carried by a person. It has a container with water with a magnetic coil around it. The magnetic coil is turned on to orient all the hydrogen protons in the H2O and then relax them. And by looking at that relaxation, you can say something about the gross magnitude of the magnetic field as you walk across to be able to get some profile that looks a bit like this. I didn't pull that up, but I bet you we can find a picture of a proton magnetometer. Or you can look it up on your own machine. Shopping, don't know shopping. Yeah, so it's something that you merely walk across the field with. It has this little assembly here, has a readout. You take it and do a profile, and you use that profile to be able to say something about what is present underneath you. Often it's, sometimes it's a bar, horizontal bar, perhaps 6 feet wide, that can be used as well. So you see them in a variety of different forms. So one method of doing it, not very useful for us because there are not very many signals that would be magnetic in the kind of systems that we're looking at. So magnetic signal of the individual rocks is a proxy for something, not very useful. Electrical signal. Well, we already said that if you have, say, a brine saturating a fracture, then that might have a high electrical conductivity, a low electrical resistivity, and maybe if you can pick that up in some way, you could be able to, by proxy, say we have a fracture, it's brine filled, it's got fluid flowing in it. Perhaps that's a good target for our reservoir to be able to use the permeability that might be present within that system. And so geoelectric methods come in 2 flavors. DC methods using direct current and electromagnetic methods using AC current, which are essentially radar, like picking a plane location by sending electromagnetic signal to it, seeing it bounce back, and then being able to use the time-distance travel relationship to be able to range on the aircraft, etc. And so we'll talk about each of those in turn. We'll talk about DC methods first. They come in 2 broad varieties. They come as methods to profile and methods to depth sound. So profiling methods means that you take a measurement and you move an array. So an individual array would be this line here, and it would have a number of electrodes that you just push into the ground with a car battery attached to it and a voltmeter, nothing more novel than that. And you'd take this array and then you'd move it parallel to it and do the same, and parallel and parallel and parallel. And this reading of the change in resistivity that you get would give you a change in resistivity reading as you go laterally along your trace, and this would tell you something about how the resistivity is changing along the length of your traverse. Alternatively, you could use, this would be profiling, as it's mentioned here. I'm not sure whether you can see that or not. The other method would be sounding, and sounding would use the idea that if you take a profile, again with some electrodes at a particular location, and if you make that profile wider, in other words, extend it out in this direction and in this direction, then all of a sudden you start looking deeper and deeper into the crust. And so if you take it out wide enough, then you can measure the resistivity with profile depth as you go down, and you record it on some trace which is really a depth versus an apparent resistivity. So in each of these cases, we'll use rho as an apparent resistivity. So apparent resistivity we can measure. So that's kind of the idea. We'll come back to that. The basic idea is this. It uses electrical conductivity or resistivity as the proxy. So it uses Ohm's law. Volts are equal to current times resistance. V equals IR, this voltage. often, if you're looking at transistors, this is a resistance, which is defined in terms of ohms. But because we're looking at materials which isn't a resistor, but is a material that has an electrical resistivity attached to it, we could think of writing this law in terms of not a resistance, R, but in terms of a specific resistivity, which is defined as the length of the resistor and its cross-sectional area Q. So this area Q is here. So if instead of having a single resistor, which would look like this, I guess, right? Between upstream and downstream. So that would be the resistance, which would look like this. If instead you measure the electrical resistance by measuring a voltage drop for a given current, you can get this, right? So you can get this for sure. If you then take this and you multiply it by the length over which your voltmeter poles were apart and the cross-sectional area of the piece of rock that you have, you end up with what's referred to as a specific resistivity. And the units of this, length squared, are in ohm meters. And it's a measure of the resistivity of the rock rather than the resistance of a single resistor, which has a single magnitude of ohms. And so specific resistivity is the characteristic that we want to measure. When specific resistivity is high, it's very resistant to current. And I guess conductance equals 1 over resistance. The reciprocal. Hydraulic conductivity, hydraulic resistivity, they're the reciprocal of each other. And conductance and resistance are the reciprocal of each other. And so the basic idea is just this, very simple. You take a 12-volt car battery, you take a piece of rebar, and you put it into the ground here, and you put it into the ground here, and you collect that up to the battery through crocodile clips. Those put a current into the ground, which flows from one electrode to the other along these streamlines. And you take a voltmeter, and the voltmeter is 2 rebar electrodes that are put between it, and you measure the voltage drop that occurs between these. If you know the current that goes in here and the voltage between these, the voltage drop between these middle locations is going to be some fraction of the total voltage drop across here. And if you think about it, you could imagine that it's this current that's flowing is, if you're taking the reading between here, then it's kind of sampling exactly what the resistivity or conductance is kind of between these electrodes. If you stretch out your array so that M and N now, instead of being 6 feet apart, are 20 feet apart, and the other electrodes have gone out further, then basically you'd be again looking at this patch, but this patch would have stretched, so now you're looking deeper. So the idea is that you take this profile with these electrodes, you expand it laterally, and so that physically it looks deeper and deeper and deeper and deeper into the characteristic below. And if you plot the magnitude of the voltage drop that you measure with the separation of these electrodes, it's really measuring the voltage drop as you go down deeper. And of course that voltage drop is in some way related to the resistivity and specific resistance. That's really all it is. And so what you do is you take these arrays. So these would be the injection electrodes, if you like. This would be where you're putting current into the ground here and here. These would be the separation between the measuring electrodes. And you could think about doing it in some arrays where you make L larger and A, so you double L and you double A, then you double L again and you double L, and you get wider and wider. And or you just expand it out to have these being equal distances apart, and you make it wider and wider. And these are referred to Schlumberger, the company, the Schlumberger brothers. The technology that their company was initially based on was electrical prospecting, or a Venner array, or a so-called dipole-dipole array. All it says is that the current electrodes on the outside and the voltage measuring ones on the inside, I guess these are outside. These are the current electrodes, these are the voltage ones. Usually they're in the middle. These are the voltage measuring electrodes. They all conform to some geometric format. And so you can plot the specific resistivity for the rock as a function of the current that you're putting into the ground. The current you're putting into the ground, the measured voltage drop between these interior electrodes, and some coefficient. And this coefficient is just a function of the geometry. The length between the current electrodes and the distance separation between the measuring electrodes. And so if you measure it at a variety of different lengths, you can make a plot of specific resistivity. So that's this term here, calculated as a function of this correction factor. These two properties are measured, and this correction factor accounts for the fact that you're widening the sample as you sit on the ground. And so the idea is that if you plot the specific resistivity that you get for this separation, if you plot the one that you get for this separation, and you plot the one you get for this separation, then these physically represent kind of soundings at a variety of different depths corresponding to these. And so this is telling you something about how specific resistivity changes as a function of depth, and you can use that just like you use a drill hole to be able to say that, oh, my specific resistivity is such and such at this depth. If I have a table that tells me what specific resistivities are as a function of different materials, I can make a guess as to what I might have at that depth. So that's the method by which it is. And so it might be that if you have a high specific resistivity, which would be a low conductivity, I guess if you had a brine, you'd expect to be a low resistivity and a high conductivity, then you'd be able to perhaps link that with the readings you get from this. So you can use it either in sounding, where you expand the array laterally to be able to do that, or you could use it in profiling, as we defined. So in other words, you have an array that is just one separation, and you physically take the template and you move it, and you move it, and you move it. And so what that would do, it would measure the resistivity at some depth right below it, constant depth. And if you plot it as you go along the length of your profile, it allows you to say something about when you get a change in resistivity. So you can use it in a couple of different modes. So if you're checking the orientation of a new road and want to know if you have some clay layers in there, you might do this. If you're trying to prospect for what things change at depth at a geothermal site, you might use sounding to be able to do that. And so that's basically the prospect of doing that. And so this is what it would look like. You'd end up with a measurement for a short separation, a larger separation, a larger separation, etc. These would just be values of, what do we say, voltage over current multiplied by some value, be these values here. And they represent, and you plot them as a function of the separation distance between your electrodes, and each of these progressively represent a different depth. So if this represents the ground surface here, then as you go down, you could think of this as being a borehole that just goes down to some much larger depth. And instead of a borehole saying what the material is, because you take it out, it says what its resistivity is in terms of ohm meters. 6 ohm meters, 4.4 ohm meters, etc. And then you attempt to try and correlate that with magnitudes of what individual materials might be that have those individual characteristics. And so it's not much use blind. You have to use it perhaps with some drilling to be able to see what the individual materials are. But of course the utility of it is if you do have a drill hole that defines exactly what you have with depth, and you can correlate that with one electrical sounding, then you could take the soundings to other parts of your site and use that to do a geoelectric borehole, if you like, to figure out exactly what happens with depth. And so that's kind of the overriding idea of it. So pretty straightforward. The problems, of course, are that you can have a single profile, but that profile is non-unique. And so that single profile might fit this geometry with a certain distribution of layers with different resistivities, or it might equally well fit this one, or this one, or this one, or this one. So the results are typically non-unique, but they have some semblance at least to each other in these 5 profiles that you see here, so at least you can make a distinction between them. And so that's basically the idea. The other way that you can use it, actually, is to, especially in shallow methods, is if you look at this being the electrodes that you put in your current, and these being the electrodes that you measure your voltages across, you could think about doing a measurement in azimuth. So you measure the resistivity along one azimuth, and then you switch it to be able to turn. And so if you have fractures, you can imagine, that might be bearing of fluids, which might be electrically conductive, you might be able to pick those up by doing that. And so we have some pictures somewhere, I guess. Yeah, I think this is the only picture I have of that, which is worthwhile seeing. Which is basically that. You can't see much here at all. You can see this little skewer here. You see a little bit of red here, which is really a crocodile crib. And the only idea is that basically you have a car battery sized box, which is a battery. You have a voltmeter, which measures the voltage, and you set it up to measure between 2 electrodes. And you can see these various electrodes that are put here. These are actually in an azimuthal array to be able to pick up changes in azimuthal resistivity within clays. Glacial clays. It's in Racine, near Wisconsin, Well, not near Wisconsin, near Racine in Wisconsin, I guess. So, geoelectric methods. The other ways that they can be used is as tomography. So ERT stands for electrical resistance tomography. Here used to look at a contaminated site, Edwards Air Force Base. I think that's where the space shuttle used to land. I guess it lands nowhere now, but it used to land there because of the long runway. And the idea is that now, if you take a contaminated region where you spilled some gasoline or other organic materials into it, then what you could do is you could drill some drill holes down through this in a perspective drawing. So drill some drill holes down through this, and within those drill holes you could put some electrical sensors, and you could do the same as we just did between 4 points. So you could put in a current between 2 locations and measure voltages, but now this, instead of being on the surface, these could be points within a borehole at some depth. So they could be within multiple boreholes. And so if you do that, then you could do tomography, just like a CAT scan in the hospital, to be able to measure a contour map between a whole bunch of resistivities that you're trying to evaluate along a plane that's between 2 boreholes. So you have electrical sensors here, electrical sensors here, you have current running between these points at different depths, and you try and make a picture of the electrical resistivity map, if you like, within this. So it's a horrible figure, it should be in color, but you can see areas of highs and lows which represent high and low electrical resistivity, and you can use it, for instance, in time lapse. Take a picture at day 1, day 5, day 20, day 40, actually these are dates I think on the top, and day 100, to see how it changes as a function of time, and that might be an indication of whether you're actually remediating the site in this particular case. So DC electrical methods is one way to do it. One of the most common methods for doing deep electrical resistivity is magnetotellurics. This is taken out of that forged report from COSO that we just talked about. And the idea is that the magnetic field of the Earth generates electrical current. And if you can pick up that current by putting a monitor on the surface, then you can do a survey that evaluates the electrical potential throughout the region at relatively deep depths, because the natural magnetic field of the Earth is the loading system. Okay, that's my message from daughter. Magnetic loading system creates the electrical current, and then you measure the electrical current in place, and so you end up with a resistivity map, which instead of being perhaps meters of scale, this is many kilometers. I can't see exactly what the distances are, but if this is COSO, the forge site, then this is kilometers on edge. This would be of the order of a couple of kilometers, 2 kilometers. So you can do these surveys that are of the order of 2 kilometers. And of course, what we've said before is that if you want to look at depth by pulling out the width of your array, then if you're able to make a measurement down to 2 kilometers depth, then you have to have a voltage put into this system of that kind of width, many kilometers in width. And so the natural loading by the magnetic field of the Earth gives you the ability to be able to sample down to that particular depth. And so the result from this particular survey at COSO is given in terms of magnetotelluric conductances at large scale. This was the actual desired site for the forge site. This is the existing COSO reservoir. I don't know in this particular case what the contours represent, because I didn't include that, but it represents behavior at half a kilometer depth. And so at a useful depth, at least in terms of a geothermal site. 2 rather exotic methods would be induced polarization. Not really used, I won't say very much about it. But again, it uses electrical resistivity as a proxy. Imagine that in an array, you put in current into the ground over some time, you leave it on for 5 seconds, then turn it off. You leave it off for 5 seconds, then you reverse the current into the ground, 5 seconds, etc. Then if you measure the decay at another location, so if you have some that are putting current into the ground and some that are measuring the voltages between them elsewhere, then if you measure the rate at which decay occurs, then you can say something about the magnitudes of the electrical resistivity in the field. And you can obviously do it at a relatively large scale, because you can get these dipole-dipole arrays quite far separated from each other. So this would be current in, current out, and this would be voltage in, voltage out measured. And this would be the secondary voltage that would be measured at this location. This would be the current that you put in at this location. And if these are far enough apart from each other, then you're measuring resistivities at quite deep depths that you might be interested in terms of a geothermal field. So DC electrical are where you have a DC current applied and a DC voltage, and you measure the response to that. This is a decaying DC signal. AC signals will give you electromagnetic methods. And so these come in 2 different flavors. One that use very low frequency electromagnetic signals. Things like the low frequency electromagnetic signals used to signal to submarines that can, because they're low frequency, they travel very long distances and therefore can be picked up at very long distances around the globe. And it relies on some kind of transmitting coil, a target which that transmitting coil induces an electrical potential in, and some measurement of the electrical field that's put up in that coil to be able to figure out exactly what the target looks like. Not used very much in geothermal. And so we won't say much more about that. And the other electromagnetic method, which is using GPR. And GPR is used primarily in shallow methods, less so in geothermal fields. But it works on the same principle as radar in terms of picking up planes. So the idea is you transmit a signal from an antenna at a location on the surface. That goes through the subsurface and bounces off a target and ends up coming back to the surface into a receiver. And so it's the same as being at the air control tower, an airplane reflecting back off the airplane. The air control tower obviously is back at the same place. This receiver may be separated by a few feet from each other, or it may just be the same unit and looking at the vertical profile. But you want some separation to be able to separate the transmitted signal from the received signal or reflected signal. And it works on the idea that it is reflected off some kind of target. And so the principle is really pretty straightforward. The velocity of radiation is equal to the length traveled over a given time. And so if you want to calculate what the length is, you can get the length merely by multiplying the velocity times the two-way travel time, or the two-way travel time divided by 2. And so what you want to do is be able to calculate this particular length. And so if you know what the two-way travel time is, so if you know how long it takes to go from here to here to here, divide it by 2 if it's almost vertical, then you get the one-way travel time. If you know the velocity, which is, I don't know, of the order of, 10 meters per nanosecond, very high velocities. That's essentially the speed of light. These are electrical waves that are traveling. If you know what this velocity is, and you know the two-way travel time, you can calculate the length of this. Simple as that. And so there are 2 features that are important. One, you want to know what the velocity is. And again, just like in the case of electrical resistivity, you can get magnitudes for the two-way travel times, or the velocities within these things. So the velocity of air is different from water, not much, and from seawater, and from sand, and from limestone, and from granite, etc. So these velocities are in meters per nanosecond. So they're not quite the speed of light, but they're close to it. They're very, very high velocities, much higher than seismic velocities. So that allows you to be able to calculate what this length would be. And the second thing you need is you need a contrast in the dielectric constant. And so if you don't have a contrast between the dielectric constant from this layer versus this layer to define this boundary here, there won't be a signal that comes off the reflection for this layer. So you need a reflection first, and to that you have to have a contrast between the different material properties of the layers. They have to have different dielectric constants. And then the individual layers you have to be able to know or be able to approximate the magnitude of the electromagnetic wave velocity in that material. You know it for radar. You can range with radar because you know the electromagnetic velocity in air is pretty close to the speed of light, etc. But in different rocks it has slightly modified velocities. Typically you use antennae which have different frequencies. And just the same as we suggested with low frequencies for electromagnetic waves that travel around the world to be able to be picked up. Low frequencies, so this is a high frequency, 40 megahertz versus 8 megahertz. If you use a lower frequency, you can usually get deeper depth penetration with these. If you use a higher frequency, you get higher resolution because your wavelength is smaller. You get more detail back. but you end up with shallower penetration as a result of the high frequency. So it's a trade-off. You want either to be able to see something deep and not very well, or something shallow in very high resolution. You can use different frequency antenna to be able to do that. The dielectric constant is merely defined as the capacitance of a material relative to the capacitance of a vacuum. So I guess a vacuum to a vacuum would be a dielectric constant of 1, has no dimensions. And as I mentioned before, you can get different penetrations based on the magnitudes of the dielectric constant. And it controls by frequency. So the idea is this. You have a source at the surface. That source finds the boundary. It reflects back to a receiver. The time taken between going here and going here, if you add those together, it gives you a two-way travel time. You divide the two-way travel time in half to get a one-way travel time, and you use length equals velocity times time. Nothing more than that. If you know the velocity of the electromagnetic wave in that material, if you know how long it took to go half the distance, half the two-way travel time, then you immediately can get the length. And that's it. And so typically what a signal will look like, this is actually one from the Arctic, is this. And so this happens to be nothing to do with geothermal. This is a frozen lake riverbed, the Mackenzie River, in February of 1981, I believe. Not I believe. And you run this transmitter and receiver across here, and these are almost like echo sounders. So it sees an interface here with the reflection. So you send the signal down, it bounces back and goes back to the receiver and gives you this blip, but it also keeps on going down and it picks up this term here as well. And so this is just a single profile for looking at the returns from a single location, the next location, etc. And so you start seeing some features here. This is the surface of the ice in this particular case. This is the bottom of the ice, this little signal here. This signal here is a channel, I suppose, right? This is a channel within the riverbed. And somewhere up here, there's another signal that goes across here. And so if you pick up these signals and with some kind of eye of faith, if you also have a drill hole that follows down here, and you know from sampling that drill hole that from 0 meters to 1 meter you went through ice, and from 1 meter, I guess there is a scale off to the left-hand side somewhere, I thought. No, it's not on here. Oh yeah, it is. This is 50, no, this is nanoseconds. I guess this is nanoseconds. So this is the two-way travel time. So these are in time travel, and you correlate it with a length due to what we just said, that velocity times time is equal to length. So if you have velocities and you have travel times, you can convert that to a length. So you know you have water down to here. This is the bed of the river. You have sand in the riverbed within a channel, and below that you have clay, which might be in this case, I don't know whether it's frozen or not. Certainly it was permafrost at this site. And so you have ground truth with the borehole to be able to say what's there, and you correlate that with your radar signal to be able to go over to it, so that now you'd be able to say with at least some confidence that you have an interface here and here and here, even though you've done no drilling. And so you can extend that all the way across this particular geometry. And so that's just using reflection using radar. Typically it's limited to maybe something like 10 meters. So it's not going to be anything other than geothermal heat pumps. You can't see much deeper than that, just because the rocks are relatively opaque to radar compared to air if you're looking in the skies. And so it's not so used for geothermal applications. However, seismic methods are. So what have we talked about? We've talked about magnetic methods, looking for iron, or magnetic susceptibility of materials. We've talked about DC methods, looking for electrical resistivity. We've talked about AC methods, looking for dielectric constant and mediating that through electric travel time, EM wave travel time. The next one is looking at acoustic velocities. So in the same way that you're listening to me and hearing me, that's the acoustic energy traveling in air at 600 miles an hour, or whatever it is. But rocks, in the same way, also have specific acoustic velocities, typically much faster than the acoustic velocity in air. And so seismic methods rely on the fact that you can try and measure the magnitudes of those acoustic velocities in the rocks under our feet. And if you can correlate something like a low velocity acoustic signal as being a fracture, which would be broken rock, and so you'd expect maybe the acoustic velocity to be less than the intact rock, then you can use it to prospect for faults that might be flow paths. And so that's the basic idea. So the idea is that you have some kind of a source that you apply on the surface. That source, if it's a hammer, or if it's a stick of dynamite, or it's a borehole that has a stick of dynamite in it, or if it's a truck that has a vibrator attached to it that couples with the surface, will send out waves that go on the surface both as P waves, compressional waves, as S waves, like a skipping rope on the surface, but they will also travel in the subsurface. And it's ones in the subsurface that we're interested in. And so we can imagine that if we have an explosion on the surface, the waves will travel through the subsurface, both as the direct wave. When the direct wave hits an interface, it will be reflected, just like your reflection is reflected from a mirror, through a particular angle, depending on the angle of incidence and angle of reflection, a bit like Bragg's law in optics. There will be a wave that is additional to the reflected wave that comes back up here. There's a wave that will be refracted along the interface, and there's one that would be diffracted at some angle that's not a straight line, but is something off that. Like looking at fish in a pond, where you see the fish, but actually the fish isn't quite there. It's at some other slightly different location, because the ray that's coming back to your eye is actually diffracted, not a linear path all the way through the surface. And so we can use the reflected wave, and we can use the refracted wave to say something about the material that's beneath our feet. So the basic idea is this. You set up on the surface a shot, which is either dynamite or a hammer or a dropped weight or a shotgun blast, actually. Shotgun shells are used as well. You set up on a profile a whole bunch of geophones on the surface at different locations. And so that when the waves come along from the surface and hit these will register something. They'll register an arrival. And so the first arrivals will end up at these geophones defining the time it took to arrive. So these will be the first arrivals. This is just time. This is amplitude. So a typical geophone is just a magnet that sits inside a coil. When the geophone moves, the magnet tries to stay static because of inertia, and the coil moves around it. Coil with a magnet moving through it generates an electrical current. that electrical current is picked up and represents the motion of the two relative to each other. And so the first motion would be the first arrival of the wave at that particular geophone. And as you get geophones that are progressively further and further away, then the first arrivals would be progressively delayed. And so if you can calculate what this time to the first arrival is, then you can use your knowledge of what's happening within this geometry in terms of the waves traveling. So typically the velocity in the upper layer is the highest, and as you go deeper, then the seismic velocities are reduced. So if the velocity in the upper layer is highest, then clearly the connection directly along the surface to this geophone may be the time that records the first arrival, which you get here. But if these, I put this the wrong way, the opposite of that. So if you're taking notes, the top layer is the slower one. As you get deeper and deeper, larger stresses, the velocities increase. So now, seismic waves that go down to this lower substrate travel on the superhighway through here much faster and then come back up to the surface. This travel time to this geophone might be faster in doing this route than coming directly on the surface. And so certainly if that's the case for this one, all these geophones later than this, the fastest route will be in this high velocity layer at depth and then back up to the surface. So we're taking use of the direct wave through here, its refraction along this interface, and then traveling back up to the surface to be able to say something about the individual arrivals that arrive at these locations. So if we now drew a line between these first arrivals, you see that these lines have two different gradients with them. The first arrivals are the ones that come from the velocity in the upper layer. The second arrivals, or the geophones that are further away, come from doing this circuitous route that spends some time in the lower layer, going very quickly, and then coming back across this upper layer to get through. And so the basic idea is kind of shown here, that if for all these geophones you plot on the vertical axis the travel time, as we just did, or the first arrivals, and you have the location of these geophones existing as physically where those geophones are along your cross-section, then the first ones would be the direct wave, which would be coming directly to the geophone like this. And those would be this magnitude and this magnitude here. And then after that, the fast way to get to these would be to go these individual routes. And so the first arrival time here would be this. And this one here would be this. And so immediately you see you have exactly that same behavior. This gradient here for the direct wave is this, and this gradient here for this inclined wave is this. And if you think about what those mean, then this represents dx, and this represents dt. And so velocity is equal to distance traveled in a given time. And so I suppose this would be equal to, running out of time, this would be 1, and this would be v. So by definition, if this is 1 and v, in the same way that we're writing this, you can get the velocity. So with these arrivals, you can get the velocity of this layer, you can get the velocity of this layer. It turns out also that this location, where it turns over from this gradient to this gradient, also gives you some information about this depth. So this point here would give you information. It would be a function of this separation of the geophones in this case. This length here would be some function of x. And so if you can imagine that you have a whole bunch of different layers and you set it out, then these would be the shot paths. These would be the first arrivals. Then if you plot up the arrivals versus distance from the geophones, in this case you have a 3-layer system which represents this geometry here. Maybe a slow layer at the top here, a faster layer underneath it, and an even faster layer underneath it. And so you can get the individual velocities of these layers from this. That tells you something about the material. And you can also, from the place where it changes over from one velocity to the other, you can get some information about the actual depths of those layers. So it's quite a useful method. So seismic exploration comes in two flavors. One is seismic refraction, which is what we've just talked about, plotting these up. And the other one is seismic reflection. So seismic reflection is just like what we talked about in terms of radar. So the idea is, as you have much deeper depths that you're interested in, you have something that has a seismic impulse. It sends a wave down to a reflector. The reflector sends it back. You have a two-way travel time, and you have velocity times time is equal to length. If you know the velocity of the material, if you know the two-way travel time, then it gives you some information about how deep that layer is. And so you just go across the surface with an array of geophones, shooting off a whole bunch of explosives. For very deep exploration, it would be in boreholes and it would be dynamite. For shallow exploration, it would be someone with a sledgehammer on a steel plate. And you get this process of the arrival times with depth that allow you to be able to reconstruct the subsurface structure. And so that's all. And so finally, again, a fourth method in terms of a proxy, not used in geothermal, gravity methods. And gravity methods use changes in the gravitational field, not the magnetic field, but the gravitational field, to be able to detect things like voids. So if you're on the DMZ in between North and South Korea, and you're worried that someone's been digging a tunnel under your feet, you take a reading of the local magnitude of the acceleration due to G, the gravitational field at that particular location, and you do a profile to measure it very accurately at a whole bunch of locations along a section. And all it uses is Newton's law of gravity that says the gravitational attraction between a small body and a big body can be measured by an applied force between those bodies, and it's what we call the gravitational constant. So the gravitational constant is just by measuring the attraction between two bodies. And so if you can measure the magnetic field very accurately, and it's done by having a gravitometer, which is just a weight on a very sensitive spring, as you go across and the gravitational attraction changes in space, the stretching of that spring changes in response to it. So if you have a big gap, which is a tunnel under your feet, then it's no longer attracted to the mass that's there, and so the spring will recede and attract you. So if you use this spring extension to be able to measure the gravitational acceleration, you can plot the gravitational acceleration along a section, and you can see where it's at a minimum or a maximum, and you might use that to be able to do something. So typically it's not very useful in the kinds of depths that we've talked about, although some people have used it on volcanoes to try and determine whether the magma that's coming up is coming up with lots of gas in it, because obviously gas will have a lower mass signature than magma that is mainly molten rock. And so you can use it in some places to make distinguishing features at depth that say something about it. The real difficulty in using it is that all the portions of the signal that tell you what the gravitational acceleration are 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 greatly swamped by things like topography, the distance of elevation from the center of the Earth, and so it's a very tricky signal to be able to measure. So we've talked about the fact that if we use geophysics, we're using a proxy measurement. Magnetic susceptibility, electrical conductivity or resistivity, dielectric constant as a reflector, and the speed of light for radar and electromagnetics, acoustic velocity and acoustic impedance, the product of density and acoustic velocity, to define differences between layers, and gravitational attraction. And we can do that from the surface to be able to say something about what's happening in the volume that's below our feet. If we want to be able to ground truth it, then one way to do it would be to drill a hole, to take samples, to take those samples back to the lab and measure acoustic velocity or electrical resistivity in the lab, which might be useful. But it turns out that in drilling holes, it's much cheaper to drill holes where you don't recover core, but you just pulverize the material in the core, in the borehole, and send the material back to the surface as cuttings, as chips. And so if that's the case, then what you could do is you could use a tool within the hole to be able to measure the characteristics in the borehole wall. And so the other place where Schlumberger makes their money would be by borehole logging. So you have a sonde. So it might be a couple of meters tall. It fits within the diameter of the borehole, and it has some tools within it. And those tools are merely dropped on a wire line all the way down to the bottom of the borehole, recording all the time as you run it down the borehole, and then taken back up and recording all the time when you come up, so that you have a profile of some signal as a function of depth as you go down. And so the signal depends on the particular sonde that you're running, and the main kinds of sondes would be these kinds of signals we have here. So you might measure the gamma ray count in the borehole as you run down, because that's a measurement of radioactivity in naturally occurring clays. And where it's high, you have clays, and where it's low, you have maybe sandstones. So you can use that as a proxy. You can measure the backscattering for a cesium source, which is a radioactive source, which tells you something about the changes in density as you go down the hole, just by looking at the backscatter. You can measure the backscatter from a neutron source within the log, which says is backscattered from the hydrogen nuclei in water, which tells you something about saturation. Or you could measure the electrical resistivity as you go down with an electrical log. And so you can imagine that on a sonde, if you put, I don't know if this is an electrical, yeah, it is an electrical one. If you had a current put in here and a current put in here, and you measure the voltage drop between two locations, you could do exactly the same as we're doing on the surface with a Venner or a Schlumberger array to be able to measure the local electrical resistivity in the vicinity of these two voltage meters. And so you could measure continuously electrical resistivity with depth. You could measure the salinity of the fluids. You could measure the temperature. You could measure the acoustic velocity at depth. You could measure the diameter of the borehole with a caliper log, which expands as it goes down and measures that expansion. You could have an impeller, a little propeller on the bottom of your sonde that spins at the velocity at which you drop the sonde down. But if you have water flowing up the hole, it will spin even faster than it should. And so dropping the sonde down and pulling it back up and measuring changes in the spin rate of that impeller give you information about whether you have fluids flowing up or down your hole. And you can also have a gyroscope in there that measures whether your hole is vertical or whether it's deviated from the vertical as it goes down. So very relatively sophisticated instruments. The idea is that you run them down the holes. They might be different SONs. You get a profile of how density, gravity, electrical conductivity, electrical resistivity, which is the reciprocal of conductivity, self-potential, I don't know what this one is, and then you combine all of these signals at a particular elevation. It could be an AI system, machine learning system, and based on the characteristics of these measurements, you come up with some interpretation of the stratigraphy. So a sandstone that's got saturated with water, which has 10 parts per million brine in it, you might be able to distinguish between all of these things by combining all these individual signals, each of which says something about what is going on. So whether it measures the radioactivity that's present in clay-rich materials, how the density changes between a sandstone or a clay, whether they're saturated, what the electrical resistivity or conductivity is, what the acoustic velocity is, etc. Caliper locks, if you have very weak materials, the borehole sloughs, and therefore the caliper reading gets larger because the borehole is broken down, and you can say something to be able to resolve behaviors. And so then you can use this information to be able to say something about the system. So the basic idea is whether you can use any of these signals to say something about it. So these are useful tables. I don't think it has geothermal energy on here representing any of these things, but you can imagine that if you do seismic profiling, or if you make gravitational measurements, or if you measure magnetic measurements, or if you measure resistivity, or if you use radar, and some of these other methods we've kind of passed on, or touched on, and then moved on, then some of these methods would be appropriate for some different kinds of explorations. And so if you want to find out where bedrock begins below the soil, then seismic methods are quite good because the contrast between acoustic velocities between soil and rock are quite high, and so they're quite distinct. But gravity wouldn't give you a very good picture for that, and sonar wouldn't either. Radar would be quite good for the reasons we talked about when we looked at the ice on the Mackenzie River. And so you can look at picking out things like fractures to be able to define characteristics in the subsurface, what methods would work and what methods might not work. And so that's kind of a potted view, if you like, a very quick view, almost from 35,000 feet in terms of what these methods might do for you. But I would say that in closing, if I can move up through here, I'll just go back to the initial pages. I don't know, will it go back? Will I do this? Yes, it goes back. If we go back to the point I made on the first page, is just to reiterate, all of these methods are proxies. They give you some information about whether you have iron in the system, what the resistivity is, what the acoustic velocity is, what the density is. And it's measurements of these measurements as proxies which allow you to say something about what's going on in the subsurface. And borehole methods are merely a way to be able to provide ground truth. The borehole says exactly what is present at each individual depth. Certainly if you have core, you can tell that. If you don't have core, you can run borehole geophysics down on the hole to be able to say how each of these signals might change as a function of depth, and gives you ability to be able to have more confidence in your interpretation of those results as you go away from the location. So that's it. So finding out what's going on. Geological habit, we talked about last time. Looking at a big site, might be kilometers on edge. You want to have a reasonable idea what might be underneath your feet. You're interested in being able to know maybe the temperature. You can't tell anything about temperature for any of these methods. You might be interested to know whether you might have flow. Flow would occur on fractures and faults. Certainly some of these methods would address whether you have those kinds of systems in the system. If you want to really know what's there, then what you can do is you can ground truth it. If you want to ground truth it, then you have to drill it. And so on Tuesday we'll talk about drilling. We'll do that remotely. And also, if you want to turn it into a geothermal field, you want to use those drill holes at some stage to be methods by which you either produce fluids or you re-inject produced fluids to be able to keep the reservoir sustained. And so the next topics we'll talk about are in terms of drilling. How do you drill in these systems, both for site investigation to understand what's there, but also to be able to develop the field. And then what might you want to do once you've got those drill holes in place to be able to see whether the field is going to be productive and sustainable. And so that's kind of the end result of this. So topic 7 is talking about that. And then after that, we'll talk individually about hydrothermal fields, about EGS, about direct use, ground sourced heat pumps, and aquifer thermal storage. So that's kind of where we're going with this in terms of applications. Okay, all right? So I should leave it there, and I should run across campus. Any questions?